module number 12, part A. So, we finished module number 11 last week. Is there any questions about that stuff? We finished up with some of your favorite things in the whole world, formulas, and we went through them. Your test features some of that stuff. Just looking, I don't think you got to do a lot of balancing this time. You just asked to describe, in some instances, the effect of temperature and pressure on the various phases. You're asked to do some molality questions, and we looked at the formula for molality, and again, it's fairly straightforward. And the only issue with regards to that is when they give you the wrong units, so you have to fix the units before you do something, or of course in the case of stoichiometry, if they give you some aspect of the a couple of aspects of the molality formula, and then you have to solve for moles, and you plug moles into the equation and compare in terms of the stoichiometric coefficients, and then ultimately solve back for grams. So is there any questions about any of that stuff? The formulas aren't hard, they're just, you gotta concentrate on what they're telling you and asking you, and go from there. Anything at all? Alrighty. So everything that I have of yours is graded and up on ThinkWave, and I will give stuff back to you today so long as we can get done. And some of you still owe me stuff, and now I'm giving you more to owe me. So it never ends, does it? So there'll be 2 pages double-sided of terms and 1 page of tasks double-sided. It's a sound all morning long. All right, page 383. Take a look. We are beginning Module 12, so we will complete Module 12 next week, of course, and then the week after that, you will begin your spring break. I believe that's how it works, isn't it? If somebody's got a syllabus, take a good, quick look. I'm pretty sure that's the case. So we will, when we get back from the break, have the last two sets of Module 13, and then do some testing, and we will wrap it up. So hard to believe how fast time flies sometimes, and you get older and you just can't believe it. Turn around twice and it's another year. But that's good because Christmas comes faster that way. So. All right, so on page 383, we are introducing the gas phase. Yeah. And in terms of gases, this is not a long module, which is maybe a good thing too. It's about 20 pages max. And sadly, for you, it's filled with formulas, but once again, I don't think they're very hard. Simple ones, as a matter of fact, just following the bouncing ball of what they give you and what they leave out and what they're asking for. So, in terms of introducing the concept of pressure, and with respect to the gas phase, again, I'm on page 383. I've defined for you pressure, which is simply the force per unit area exerted on an object. So, and there is the formula for that, and as a matter of fact, you won't be asked to use this formula at all. It's just a way of sort of thinking about what it means to have pressure. And no, I'm not talking about what happens when your girlfriend wants you to go see the Nutcracker, or when your boyfriend wants you to go watch his soccer match. No, not that kind of pressure. I'm talking about the kind of pressure where there is some other form of force upon something, and that is what then results in what we describe as pressure. So the kinetic theory of matter, as you will remember, and I'm just reading from your notes, and if you would turn over to page 384, 85, and we'll introduce the units in just a second, but I wanted to refresh you. Again, each module, I just love to say it. That's why I do. Why else would I say this? But I just love to say it. So the course, I don't offer cumulative exams, but that course is cumulative. Yeah, it is. It keeps building on itself. So we talked about the kinetic theory of matter, that molecules make up a substance and they're constantly moving. We said that solid molecules just, right there, you don't see much movement with regards to this podium. It's made out of wood, but it is, in fact, in motion. The molecules, the wood molecules, are simply vibrating back and forth. You understand the aspect of motion better with regards to liquids, because you can see them. They move around in their container, and the molecules, though, are still relatively close to one another, even with regards to a liquid. But then gas molecules move around in their container, and they stay, by definition, far apart. And you know that to be the case. If you boil water, you see the steam come off the water and it sort of dissipates. It actually evaporates in some instances. But the bottom line to it is, you know that gas molecules want to stay far apart. Well, as it turns out, gas molecules exert a force or a pressure on everything around them. You know, as we began the course as well, we talked about what the study of chemistry is, and it's the study of matter. And I'm certain, because I pretty much do every year, asked you if what matter was, and I think I asked you if the air you breathe in and then that horrible pollutant that you breathe back out, if that was matter. And most of you correctly said yes, it is, and it is simply in the form of gas. So that gas is exerting a pressure on you and everything around you. As a matter of fact, atmospheric gases exert force on every living creature, every object on earth. And you know, you don't think about that a lot, do you? I mean, I don't, except some of you who notice when when fronts move through and you get these nasty sinus headaches, and you know a front is moving through because you know you can almost predict them sometime. Anybody here get them things? Anybody here have, you know what I'm talking about? I mean, I have, it's the only headache I've ever had in my life is a sinus headache, and pressure changes, although we will see, though relatively minor, can have a real effect upon you. Anybody here baseball fan? Anybody like baseball? Yeah. Go-karts. So anyway, don't tell me. Braves fan? Yeah. I'm just kidding. But anyway, I'm best friends of big Braves fans. And you know, they signed Ozuna, so it just figures. So. But anyway, so if you play ball most places around the country, the environment is pretty similar. I mean, baseball parks differ in size and various things, but most of the time they're different until you fly out to play the Rockies in Colorado. All right, and they are in, where do the Rockies play? What's the city? I can't even think of it now. But anyway, they play in the mountains. That's a couple of thousand feet up there. And the ball carries a lot differently in Colorado, wherever that is, whatever city. Isn't that terrible? Can't think of it. Than it does pretty much anywhere else around the country. And so you got guys who play in Colorado and half of their games a year are there, and the pressure differences upon the ball, if they're good hitters, you know, elevates their batting average maybe 30, 40 points. They're able to hit more home runs in Colorado. And the opposite is if you're a pitcher, particularly if you're somebody that relies on cutting the ball or curving the ball, it don't cut and it don't curve in Colorado like it does anywhere else around the country. It's pretty much just throw a dead ball. Guy signed there, man named Hampton years ago. He was an all-star for Houston. And he signs this incredible contract and plays in Colorado, and he stinks the place up. He was awful because he's a lefty and he threw a lot of movement type pitches, and they don't move there. But anyway, the point of all of this is to help you think about the fact that right now there is pressure being exerted on you in terms of aspects of the creation that very often we don't think of. Once again, easy to think of. Who here has flown? Everybody in here flown? Yeah, gotten on a plane. And so the plane goes up, and what happens to your sinuses, you know? If you're not chewing gum and if you're not swallowing, you immediately Yes, sir.
One of the things they'll tell you, especially in small airplanes, if you go, don't take anything like a bag of chips or some applesauce or something like that, because all the containers explode.
How about that? That's interesting. Hadn't thought about that. That's right.
I want to take a bag of chips on a plane.
I did it one time and it exploded. It took me 30 minutes to clean out this little bitty bag of chips out of this airplane.
For heaven's sakes, and it exploded.
It exploded. We were up like 10,000 feet. But
Wow.
it was-
Because those planes aren't pressurized.
The small ones aren't.
Right. How about that? How about that? I've flown in one time. A buddy of mine was a pilot and insisted on taking me up, and I've never been a fan of the little guys. Just haven't. I mean, they're fine and very safe, but all right, and thank you for that. That's an excellent illustration again. So, varying differences in terms of pressure. Well, what I just said about my sinuses, I'm going to make a statement that seems to contradict it, but it doesn't, because even small variances can affect my sinuses. So, right in the middle of page 1, atmospheric pressure is relatively constant. It's 101.3 kilopascals. As it turns out, Pascal was a marvelous scientist, and the particular unit here is named after him. The discussion of Pascal is at the bottom of page 383. Interesting guy, a fervent believer. As a matter of fact, if any of you have gone a little deeper in terms of your faith and in terms of your study, there is a term, it's called apologetics, which doesn't mean, I'm sorry that I believe in Jesus, I'm sorry. No, that's not that type of apologizing. It means defending the faith. And Pascal actually has all those hundreds of years ago produced proofs in terms of the Christian faith that stand till this day. He's a brilliant guy. But anyway, so kilopascals is the unit. Since atmospheric pressure is relatively constant, its value has become a unit for measuring pressure. So again, what I just said about the changes in pressure around the country in various places, still atmospheric pressure is relatively constant. It is not constant in the sense that it never changes, and as I mentioned, slight changes can have real impacts upon us. But for the most part, and especially for our purposes in chemistry, we are going to describe it as a constant, and it equals 101.3 kilopascals. So there you go. 1 atmosphere is equivalent to 101.3 kilopascals. And so here's a couple of other units. And once again, why do we offer these differing units? Simply to confuse you. I mean, there's no other reason for it. We love to do these sorts of things in the various courses, and so we add in extra units here for that purpose, just to confuse you, and to, at some point in time when you're trying to figure these things out, make you pull a lot of hair. You all have a lot of hair, but you can see there's been a lot of confusion in my life, so I have very little hair left. But anyway, kidding aside, the various units in terms of measuring pressure are millimeters of mercury, small m, small m, Hg, the formula, the symbol for mercury, and torrs, T-O-R-R. All right, and the way that works out is 760 torrs equals 1 atmosphere, and 760 millimeters of mercury equals 1 atmosphere. All right, so we've got 3 different pressure units: kilopascals, torrs, and millimeters of mercury. And of course, true to form, I want you to memorize them, right? Right? No. But as you work with them, you're going to remember some of that stuff, especially since, 760 goes twice for millimeters of mercury and for torrs. So that might be a little easier to get. So on the bottom of page 384, there is the introductory material about Boyle's law. So as it turns out, Robert Boyle was actually another wonderful believer. And as a matter of fact, Boyle, in terms of what he did, his determination, he was interested, there was this whole deal, I think it's called alchemy. Isn't that what it was? I can't remember exactly, but I'm pretty sure that's the term for it. But that was the desire in the Middle Ages to find, alchemy, to figure out a way to turn common metals, lead, for instance, into gold. It's a great job if you can do it, you know. And so a lot of what was done in the area of, in quotes, science was to figure out a way to turn whatever you might have around the house into gold. And of course it didn't work. But early on, Boyle decided that that wasn't going to be his life's calling. He would rather pursue true science and do that to the glory of God. So again, these days, and the author here makes the point, you guys go on to a state university, you'll find some believers in the science departments, and you'll find some folks who are not. And the believers most of the time, especially in these days, they're pretty cool about it. They don't stand up on the soapbox, so to speak. But you'll find out one way or another, especially by the way they teach, and then the non-believers will jam it right up your nose, And the sad part about this is the number of non-believers in the fields of, quote, science, and that was not the case 300-400 years ago. Science was predominantly done by people who understood that there's a creator God who has created in a way that is logical, that can be pursued and learned in terms of his creation. So that's no extra charge for that little comment there. So Boyle, in terms of what he did, was pretty much portrayed by the picture. Oh, we love the pictures. On page 385. So what you have there in terms of identifying Boyle's law, you've got three different pressures in the form of three different weights on top of a closed system with a gas inside. All right? So if you've got a small pressure or a small weight to the left, you see what's going on there in terms of that mass that's exerting the pressure. You can see it in the picture and experience it in your mind's eye in terms of if you don't have a lot of pressure on a gas, the little doodad there at the top is not going to go down far. Well, you add more weight, you add more mass to that, and lo and behold, it sinks further down into the container, and the gas is compressed more, right? So that movement of those molecules has been diminished to some degree. Well, we're going to add even more to that thing, and lo and behold, now we've changed the volume of that gas even more. So fairly obvious in terms of what we would think about these things. If you compress gas, you're going to diminish its overall volume, and that's pretty much what Boyle said. Pressure times volume actually equals a constant. And what he means there is, and we're going to see that in the very next statement here in terms of the ratio, the way this works at the bottom of your notes. So when you have a small amount of pressure and you have a certain amount of volume of gas, when you increase that amount of pressure by virtue of increasing the mass, you do so in a way that directly affects the ratio of that volume. So, in other words, every time you change the mass, you're going to change the volume, and when you multiply the two of them, the answer is still going to be the same. It's a constant. All right? So nothing changes. It's all in ratio. As you add a weight or mass and change that pressure, you're going to change that volume as well, and the multiplying the two of them together will yield the same answer. So that's what you've got there in terms of your notes. If pressure increases, then volume decreases, and vice versa. The reason for this is because greater volume allows gas molecules to spread out further, so there's fewer collisions, and therefore lower pressure. Less volume means more collisions and higher pressure. All right? So that's what we got going on. Now, there's another way to state Boyle's law. And as I say, we just love the formulas, don't we? And it's simply a ratio question. Some of you missed what did we do at the end of, what do we call it? But it was just ratios. Some of you did. Maybe you need to look over that, this idea, this concept in terms of the dilution stuff. M1 V1 equals M2 V2. Some of you messed that up, and it's really simple. It's just, again, trying to figure out what you have in terms of in this case, P1 V1, and then solving for P2 V2 or whatever they might give you in the process. So, again, in terms of looking at the other way to understand Boyle's law, that's the point. So, equating this to the pictures, say pressure 1 is in the left side picture with the small amount of mass, and volume 1 is the large amount of mass. Well, that's in an exact ratio to the picture on the right side of figure 12.1 in terms of the larger amount of mass and the smaller amount of volume. They equal one another as you multiply them together. And so therefore, as we love to do, you can solve for any of those so long as you're given 3 of them, right? You just change the equation around so that you end up solving for 1. So let me pause there and see if there's any questions about Boyle's law and concepts of pressure and volume. And incidentally, I did not make this statement, and it's vital to do that because we're about ready to discuss it now. Boyle's law works with constant temperature. So, in other words, if you're not changing the temperature, then volume times pressure equals a constant. And then V1 P1 equals V2 P2. Temperature must remain constant in terms of discussing Boyle's law. All right? Questions about that? Yes?
And how does that work in an airplane? Because the air gets colder as you get higher, correct?
What's that?
The air gets colder as it gets higher. So
Yes. Yes.
How does that work?
Yes. We're going there right now. Excellent question. That really is good thinking. You've anticipated one of the variables with regards to all of these discussions, and in this instance, pressure and volume. So very good. And we're going there right now, thanks to Mr. Charles. All right. And as a matter of fact, he is a French scientist, Jacques Charles. And he built upon what Boyle had talked about in terms of volume and pressure, but he wanted to look at aspects of temperature as it relates to those variables. And as you can, once again, I'm sure you can intuit, you know that temperature has an effect on those two variables. And so let's just discuss it. As you might be able to figure too, Jacques Charles was a French scientist. And so his law simply says that when a gas's temperature is raised under conditions of constant pressure, in other words, when pressure doesn't change, then the volume occupied by the gas increases. And to further discuss your question, Aaliyah, actually hold on one more step, because what we're going to do in just a second is we're going to combine Boyle and Charles, all right? It's going to be char-boiled, all right? But anyway, it's going to be the combined gas law, char-boiled.
Is that what it's called?
Say what?
Is that what it's called?
No. But, you know, it's a way to remember stuff. So, I discovered the difference a teacher can make, and I wouldn't, you know, try to equate myself to anybody. I hated history. I just hated history when I was in high school. I thought it was, I mean, I slept through classes to begin with, but history was, I just never saw the importance, you know, the idea that history was, you know, you're doomed to repeat itself if you don't learn from it. That didn't cross my mind. Till this guy in junior college, it took this, it was a year of American history, first semester and second semester. And the second, he used to do stuff like this. So he was talking about Mao Zedong. Anybody here know who Mao Zedong is? You know who that is? Anybody? You know who Mao is, son? So he's the guy that took China from, it was kind of a feudal country, locally run by sort of local, what we describe as kings or something like that. And it was largely democratic, and after World War II, he took it into communism, all right, and created the society that has led to what we're now seeing today in terms of China challenging the world. And that would be fine. Any nation in terms of its rising powers, you know, do what it wants to do. But the problem is communism is inherently authoritarian and dictatorial, and so you have very little freedom under it. But anyway, so he's discussing Mao Zedong, all right? And it's spelled M-A-O, and I don't even remember how, that's the first part of his name. He's mostly known as Mao. And then I think it's Z-E, and I think it's D-U-N-G. I think that's how you spell his name. But he's talking about Mao Zedong, and just describing what Mao Zedong was doing, okay? G-U-E, there we go. And turns around, and there we go. Mousy tongue. Now, I guess that has no significance for you guys whatsoever, but it made all of us laugh. And I've always remembered mousy tongue, thanks to my history teacher, who I can't even remember his name. But so there you go, char-boiled. Maybe we'll remember the combined gas law, which is really what it's called, and we're going to get there in just a minute. So Boyle simply says that at constant pressure, the temperature and volume are linearly proportional. In the same way that Boyle said pressure and volume were proportional, well, Charles says the same thing, only instead of multiplying them, it's volume divided by temperature. It's volume over temperature equals a constant. And again, V is for volume and T for temperature. So if the temperature of a gas increases, of course, would you please take a look at page 387? There's another wonderful drawing there for you. We love the pictures. So if the temperature of a gas increases, you know what's going on. You're increasing the movement of the molecules. And so what's going to happen then at a constant pressure, and notice they've drawn the little weights on top of the enclosed cylinder to be the exact same size, so pressure is the same. But you know, if you raise the temperature, you're going to increase the volume of a particular gas. And the same thing, if you decrease the temperature, if you drop that puppy into ice water, what's going to happen is the volume is going to decrease at the same pressure. All right, and the reason is what we've learned in the last several modules If the temperature of a gas increases, the gas molecules have more energy and they want to move around quickly. I've got lots of energy. I've got to move. I got to move. And the only way the gas can move around more quickly without making more collisions with other objects, in other words, raising the pressure, is to spread out and occupy a larger volume, thus keeping the pressure from rising. All right? So again, pressure has to do with collisions, and the only way to avoid changing that is to change the volume if you increase the temperature. So there we go. We've got, once again, this related formula in the sense that you've got V1 over T1 equals V2 over T2. It's, once again, a simple ratio question. So if you're given V1 and T1 and you're given V2, you can very easily solve for T2. Now, remember we talked about the Kelvin unit in temperature. And back when we introduced that, I took you to page 387 and you looked at this and you said, I have no idea what that means. No, you got a grasp of what we were talking about Kelvin, in the sense that it is an absolute temperature scale. Oh, yes, ma'am.
Okay, so he's got me obsessed with the chip thing. So the airplane is at its own temperature, but if I attach the chip bag to a little drone and I took the drone high in the sky, would it not explode because the temperature is decreasing the gas in the chip bag, and the pressure like matches the pressure and it doesn't explode, or would it still explode?
Excellent question. If you can just hold it. I promised and I failed to deliver, Aaliyah. I said the next concept would address it. Well, as it turns out, it's got to be the charbroiled. It's the gas, it's the combined gas law that will address your question. And that's next. And I promise I'm going to come through for you this time. But your question's just excellent. And I, again, appreciate your thinking. So, again, we're wanting to know the relationship between all three. So, when temperature changes, when pressure changes, and when volume changes, okay? What temperature changes and pressure changes due to volume? That's pretty much what you're asking. And we're going to see that thanks to the fact that we can take Charles and Boyle and combine them in order to ask those questions. So you're sitting with a bag of chips at a certain temperature and pressure, and the volume of that bag of chips is just what it is. But then you take that bag of chips at the same volume and you put it in a plane where you have differences now in both pressure and temperature. So what's going to happen? And that's what we can solve by virtue of our next equation. So I can give you specific answers. I can tell you how far the chips will travel once the bag explodes. No, I'm just kidding. But great thinking, actually with both of you. But look at the figure at 12.3 on the bottom of page 387. So we talked about the fact that the Kelvin temperature scale is a absolute temperature scale in the sense that it can never go negative. And that was the issue, because some aspects of chemistry and these wonderful formulas require that you have a temperature that never goes negative, all right? And so we devised a temperature scale to accomplish that, because as you understand, Celsius or centigrade and Fahrenheit, they go negative, all right? Yeah, negative. Why are you so negative all the time? Kelvin's never negative, all right? Kelvin's always positive. And this is why. Look at what we're talking about here with respect to Boyle. Remember, Boyle addresses, what a great name for a guy who talks about temperature, all right? Boyle. But Boyle didn't address temperature, but Charles does. And you see volume in terms of our discussions with respect to Charles, and temperature, and look at the scale. So in terms of that straightforward ratio, all right, we said that if you change temperature, you're going to change, in this instance, in Charles, you're going to change volume to the exact same degree. So because of that, because it's always a constant, you can also understand now that you're going to have a straight line as you do that, as you graph it. All right? So look to the left there. There's volume. Say your volume is, it's in liters, 2.5 liters. You go all the way over to helium at 2.5 liters, and you're sitting, say, what is it, about minus, what would that be? About minus 70, something like that. I'm just, of course, interpolating a degree centigrade. But all the way down, every time you change temperature, or vice versa, you change volume, you change temperature. So, in terms of these experiments, as they drop the temperature on helium, there it is. It has that type of decrease in volume, and graphically it's a straight line. Well, guess what? It's the same thing for methane gas, CH4. As you drop the temperature, the volume decreases in the straight ratio, an equivalent ratio, and it's a straight line. And the same thing there for hydrogen, H2. It decreases at a straight line. And look at where all the lines point. As a matter of fact, everything known to humanity decreases and aims for, they're all going to the same destination. Minus 273 degrees, 273.15 degrees centigrade, which means 0 degrees Kelvin. All right, that's where the Kelvin scale starts, is minus 273.15. Well, notice the dotted lines near the end. Now that has to do with two things. Number one, the ability, the complexity of being able to drop various elements and compounds to that temperature. In some instances it's been able to happen, and in some instances you just can't. You can't get it any lower than the volumes there listed. In this instance, about, in terms of, it's even hard to extrapolate, but anyway, in terms of 250 degrees, minus 250 centigrade, that's the lowest temperature you can get in terms of a lot of these compounds. So it turns out the lowest temperature that's ever been reached is 0.1234561 degrees Kelvin. All right, so it's what is that? 1 millionth, I think, degree Kelvin. So the point of all of this is they never get to 273.15. And why is that? Why? What would happen if, based on these straight lines where everything meets at a straight line and they all meet at minus 273.15 degrees Celsius, what would happen if they ever got there? Look at the volume scale. What is at 273.15 degrees minus 273.15? What's the volume? Say what?
Nothing.
Exactly. Can you ever destroy matter? Because if you got to 0 volume, you're talking about 0 something, right? It's gone. And the point is, you can't destroy matter. You can never, ever, ever get to the point where you have no volume. So they know for a fact that you can't get any lower than minus 273.15 degrees Celsius or centigrade. So isn't that cool? I do find that sort of interesting in terms of the way the world works, and in tandem in terms of these things. Well, you know what, Aaliyah, you're gonna hate me. You're gonna go home and tell your parents, I just can't believe he did this. I can't believe that he actually did not finish this, but I'm not. We're gonna leave the combined gas law for next week. We're gonna put Boyle and we're gonna put Charles together and answer your question in terms of what it looks like for that volume change in that bag of chips. I just want to be able to get your work, number one, and hand some of it back as well. So is there any questions about this stuff? In terms of the combined gas law, we will look at that next time. Any questions? All right. So you've got your tests. That'll be due next week. I didn't quite make it past page 2. Let's see. There we go. I think yeah, we'll be okay though. We'll just hustle a little bit the next time. I'm going to call your name, and if you would, come up and get your stuff. And any